So this is part 2 from heteroscedasticity, that is interpretation of the graphical presentation of the assumption that is the homoscedasticity, increasing variance, decreasing variance, increasing and decreasing variance both are considered, that there is heteroscedasticity problem. If sigma u square is not constant, that means we know that the expected value of ui square is equal to sigma u square. It's non-constant, but it depends on the value of x or explanatory variable, that is sigma u square is equal to f of xi from this line. And in case of heteroscedasticity, it's shown by the increasing or decreasing dispersions of the observation from the regression line. That is, in this diagram, in the first diagram, this is considered as homoscedasticity, but in the second case, this is the problem of heteroscedasticity. It is increasing heteroscedasticity problem, and this is decreasing heteroscedasticity problem. The pattern of the scatter diagram depends on the form of heteroscedasticity, that is the form of relationship between sigma u square and xi, that is explanatory variable. We form the case of increasing variance of the error term as x increase. This is the common form of heteroscedasticity assumed in econometric application. And some consequence of heteroscedasticity problem, that these are: if the assumption of the homoscedastic disturbance is not fulfilled, we have the following consequence. First one is, if the error it's heteroscedastic, the u it's heteroscedastic, the ordinary least square estimation do not have the minimum variance property in the class of unbiased estimation, that is they are inefficient in small sample. Furthermore, they are inefficient in the large sample, that is asymptotically inefficient. The coefficient estimates would still be statistically unbiased. Even if the u, that means error terms, are heteroscedastics, the beta, the coefficients will have no statistical bias. So how to detect this heteroscedasticity problem? Here consider the consequence to problem or to consequence, and next consider the detection. How to detect heteroscedasticity problem? There are so many tests we can detect. These are Glaser test, rank correlation test, Goldfield quant test, Bruce Pagan Godfrey test, White general heteroscedasticity test. But here only consider the Goldfield quant test. The popular method is applicable if one assumption that the heteroscedasticity variance sigma ui square is positively related to one of the explanatory variable in the regression model. Consider the usual two variable model, that is yi equal to beta 1 beta 2 xi plus ui. Here beta 1 beta 2 are coefficient. Beta 1 it's intercept, beta 2 its coefficient, x is explanatory variable, and u it's the error term. So suppose sigma I square is positively related to xi, as sigma I square is equal to sigma square xi square, where sigma square is constant. This list is applicable. This list is applicable to large sample. The observation must be at least twice as many as the parameters to be estimated. The test assumptions normality and serially independent with UIs. H naught its youths are homoscedastics. H1 youths are heteroscedastics. There is increasing variance in the alternative hypothesis. So there is followed some steps, that is these are: we order ascending the observations according to the magnitude of the explanatory variable x. Order must be ascending. We select arbitrary a central number, that is c, of the central number of observations which is omitted from the So if the calculated value is greater than tabulated value, we will accept that there is heteroscedasticity, and if calculated value is less than tabulated value, we accept that use are the homoscedastic. That means in the first case there is a problem of heteroscedasticity, but if calculated value is lesser than the tabulated value, there is homoscedasticity. We accept that that the variance is homoscedastic or variance is constant.